The motion studied in this lab is important because it helps us to better understand the core concepts of physics that influence motion all around us at all times. The key concept used to analyze the motion is Newton's second law. This law states that a change in momentum means that there is a net force acting on the object. In the case of the falling slinky, we observe that the slinky falling downwards from rest, which signifies a change in momentum and therefore the force of gravity acting on it. This law can also be manipulated into two equations that are depicted below that can help us find the new velocity and position of an object after the force has acted on it and the momentum has changed. In order to obtain observational data, I took a video of a slinky drop from YouTube and put it in the tracker. To calibrate the video, I needed the known measurement of something in the video, but seeing as I had no previously known or easily obtainable measurements at my disposal, I used the average height of a man, which is approximately 1.8 meters, as my calibration measurement. I then set the axes to be at the top part of the stretched out slinky and used the point mass tool to track the slinky's motion. To model the same motion and to get a better idea of how the slinky was moving, as shown in the video, I created a glow script model of the falling motion. The motion I set up in this model depicts the whole slinky as the ball, so the motion shown in the model only shows a falling motion at the end when the whole compressed slinky falls. This makes sense because while the slinky is stretched out, the top of the slinky is initially falling. The force of gravity acting on the bottom of the slinky is balanced by the tension force acting on the stretched out slinky. Because these forces are equal in magnitude and opposite in direction, the slinky as a whole doesn't actually move until it is fully compressed. There is no more tension force, and the only force left acting on the system is the force of gravity. To model this motion in the computer model, I had to set the position of the ball to be the bottom of the stretched out slinky. I then had the ball start in static equilibrium, which is reflected by the initial velocity of both the top and bottom of the slinky being 0. I then set the net force to equal the sum of the tension force and the force of gravity, creating two while loops. One that updates the position and velocity while the slinky is compressing, and the other that to update the position and velocity after it is fully compressed. As you can see from the data and the comparison of the data on the graphs of the two lines, though the graphs slightly differ at the end, they both model a similar pattern of the slinky having no motion until it is fully compressed, at which then it will fall. The most likely explanation for the difference in the data is that the computer model is able to predict the motion of the slinky in perfect conditions, whereas replicating perfect conditions in the experimental model is nearly impossible. Air resistance, among other things, are out of control in the real-world models, so the conditions sometimes differ, causing the somewhat skewed data. So one of the questions that I wanted to answer is whether the bottom of the slinky in the computer model stays stationary just like it does in the video. As we can see from the graphs and the graphics shown by my model, is showing that the tension force in the slinky, while it's stretched, is equal to the magnitude and the opposite direction to the force of gravity acting on the slinky. The bottom of the slinky stays stationary until the slinky compresses, and there is no more tension force to counteract the force of gravity.